All right, everybody, it is 2 o'clock and good afternoon and hello. It's great to see you all again. I hope that you had a wonderful week off last week. Hopefully, how many of you feel more rested now than before we went off the break? Okay, that's the way it's supposed to be, right? I mean, hopefully you had a chance to rest. Try not to give you too much work to do last week. I think we all were ready for a little break. But I also noticed sometimes that we have all this momentum going, crank, and then we take a week off, and it's kind of hard to come back sometimes and get the motor going again. But we do have a fairly quick turnaround on needing to get really into prime shape for the end of the semester. As you all know, we only have 2 weeks of classes. You only have to listen to me 3 more times. It's amazing. Don't look so happy about that. Anyway, yeah, we are getting close to the end. A couple things to remind you about. We do have a midterm coming up actually before our final. The way this is supposed to work, the way I design it to work, is for you to prepare well for next week's midterm so that the following week you are already well on your way to being ready for the final. Because let's face it, the material in these last 3 or 4 chapters of the course really use almost everything that we learned up to this point. So it is sort of brought back up into the forefront of our mind just in studying for the 3rd midterm. We should get ourselves into good shape for the final. The midterm, let me just remind you really quickly, we'll do a quick review here. This is next Tuesday. So 1 week from right now, we have our 3rd test. And I pulled up on the screen here all of the usual resources for this upcoming exam. There are 2 sample midterms. One of them is in the all lowercase. The other one is in the all caps letters, along with solutions. There is also a review packet. The review packet just has like a summary of like all the important words and the things you should be able to do. There are some practice problems in the review packet as well, but I would put those kind of as lower priority compared to everything else. But I do have the solutions to those also, if you're interested in them. And then there's also here in the middle, I've got review session. And if you want, you can just read the review session and the answers to the problems in the review session. But because I had such a good turnout for the 2nd exam when I did a review session, I am going to do review sessions for this exam as well. So the review sessions, these are optional, and I will record them. So if you cannot come or don't want to come, it's totally okay. You can just take the YouTube links that I send out and watch those later. But if you're around on Sunday, starting at 3 p.m., this will be in this room. I'm going to be here on Sunday afternoon. It's going to be about 2.5 hours long is my guess, something like that. And then if you can't make that or don't want to come on Sunday, you can also come on Monday. The Monday one will be in the evening, starting at 7 o'clock. And for that one, I have to use the big classroom down in the basement because this room is not available in the evenings on Monday. So pretty much the same stuff in both review sessions. You don't need to come at all, but if you do come one time, would probably be more than enough. But you can come twice if you want. You just like hanging out. But make sure you do save some time to work on your own on some of this stuff. These sample exams especially. I would try at least one of them. And depending on how that goes, you might even feel like you want to try them both. There'd be nothing wrong with that. But anyway, if we can work really hard to get ready for this midterm, it'll pay off well for the following week as well when we have our final exam coming up. So that's kind of where we're at. There is one homework assignment this week, just one. I know that's kind of unusual. And this one is number 23. This is due on Friday. This is our 2nd to last assignment of the semester. If you get an early start on it before Thursday, I'll be able to answer questions, help you with it a little bit on Thursday in class. Otherwise, I always have my office hours. Today, I have a lot of office hours tonight, and then also on Thursday, and actually also on Friday, I will be around. So if you've got questions about this week's material, be sure to ask me. The homework covers 9.4 and 9.5, which we will completely finish 9.4 today. 9.5, we will not probably really get that far into it. You may have to wait until Thursday for that. But it's okay. There's not that many problems to do. I think you'll be able to handle it even on pretty short notice. Okay, so that I think that's most of my announcements. I hope I'm not forgetting anything. Does anybody have any questions about any of that? Yeah, hand. Oh, I just thought of something I forgot, but go ahead.
Well, I have two questions.
Okay.
One is, what about the extra credit quiz? Then the second one is, can you write the time for the two finals?
Okay, yes, okay, I forgot about the extra credit quiz. That is right. Most of you have already earned extra credit for watching a video a couple of weeks ago. And as with the other midterms, there will also be more extra credit this week coming in the form of a quiz. I just got back from LAX 12 hours ago, and I'm still a little bit jet lagged, I guess. I guess I'll use that as my excuse. Anyway, I haven't quite got my head around exactly what the extra credit quiz is going to look like. I will send that out sometime, obviously, in the next 7 days for you, and it'll probably give you another chance for 3 or 4 more points on the upcoming midterm. As far as the final exam goes, you're going to get to choose whether you want to take it on Tuesday or Thursday. Our official time is, I believe, on Thursday. I think it's from 3 to 5. I will have to double check that. I think it's Thursday. It's either from 3 to 5 or it's from 1 to 3. But I think it's from 3 to 5. I'll confirm that. Yeah. The other time would be Tuesday in the morning. And I believe that time slot is from 9 to 11 in the morning. So I will let people pick and choose whichever time they would rather take this final. And I'll make sure I have enough seats for whatever happens. If everybody shows up from both of my classes at the same time, well, I've got to have enough chairs for that. I'll make sure I do. Okay, anyway, I'll get back to that maybe on Thursday. Okay. Anything else? Well, I always start off class with a recap of where we left off in the past class. I want to be really diligent about it today because it has been 12 days since we got together, and plenty of time to forget stuff while we're eating turkey. And I did a turkey trot, believe it or not, with my whole family. They all wanted to go do it, so I went out running. I don't usually run. I usually hike mountains slowly. But this was a chance to jog, and I was over in Illinois. It was about 30 degrees, the wind blowing 20 miles an hour. It was really miserable. I was like freezing the whole time. But I did manage to finish the race. I finished in 9th place for my age group. Wow. Out of 9 people. No, just kidding. There was actually a lot of people there. There were my mom did it. She's 80 and she walked it, but she made it through, and it was good. So it's the first time I've ever done one of those. Anyway, I hope you guys had a good break as well. I actually kind of like it in the fall when they put the break closer to the end of the semester. In the spring, it's like you have spring break and then you got to come back for 2 more months. We only have 2 more weeks. It's amazing. Anyway, I am going to be diligent about this recap because it has been a while. Guys, in chapter 9, our big mission is to solve linear systems of differential equations. That means there are many unknown functions in our problem. They're all being housed in this vector function x. So notice that x is a vector, and it's drawn normally as a column, and the unknown functions are laid out into a single column, and your goal is to solve for all of them. Your goal is to solve for x. And this is the way the linear system is formatted in its most concise notation, right? Remember that A will be an n by n matrix. It's a square matrix. And the absolutely incredible thing that we saw just in the week before we took our break is that somehow the eigenvalues and eigenvectors of the matrix A has something to do with making solutions to our system. And we actually showed that. So I'm not going to repeat that right now, but if you go back before Thanksgiving break, we took these solutions, e to the lambda t times v, and we plugged them in on the left and we plugged them in on the right of our system here in the box, and it works. It actually works if you take if you take an eigenvalue, eigenvector pair for your matrix, you can build solutions like that using this e to the lambda t times v approach. Now, if your matrix is not defective, this is going to be a good review of chapter 7, by the way, right? If your matrix is not defective, then what that means is that there will be n linearly independent eigenvectors. Those are these VIs, right? V1, V2, V3. And from those eigenvectors, we can build n linearly independent solutions to our system, which is exactly how many we need. Because remember that and this goes back to before the break as well, the solutions to our system forms an n-dimensional vector space. N-dimensional. So I need n basis solutions. Well, as long as you have a non-defective matrix, you'll be able to get n basis solutions right here. And we actually checked using the Wronskian, if you remember. We used the Wronskian to confirm that these n solutions will, in fact, be linearly independent, which means they form a basis for your entire solution space. Right. So it's super easy. In fact, 90% of the work in solving our linear system over here is really finding the eigenvalues and eigenvectors, which we learned how to do 2 chapters ago. We really know most of what we need to know already from the earlier theory of eigenvalues and eigenvectors. Okay, so that's just a quick review. I did an example before Thanksgiving break, but I would like to do another one just because it has been a while. So let's try to practice one example here again to kind of get warmed up in this post-break time frame. So let's say that I ask you to solve the system. And I'm going to write out the equations like this. X1 prime of t equals x1 plus 6x2. And x2 prime of t is equal to 2x1 plus 5x2. Okay. So here I have 2 unknown functions, and they are related to each other in this system of differential equations. Now, if the problem is phrased in this way, you notice that the matrix capital A that I keep talking about over here is not being referenced yet. So I'm just going to start in my solution by doing one quick step at the beginning, and I'm going to rewrite this system. I'm going to rewrite this as the following. I'm going to take my left-hand column and just write it as the derivative of x, right? So this column here is x1 prime and x2 prime. Okay, and then the matrix, obviously, actually, the matrix just comes from grabbing the coefficients of this system. So you can make the matrix straight off of the numbers that are in the system. So 1 and 6 on the first row, 2 and 5 on the second row, and then the vector x would be on the right side. So this is obviously right here is your matrix A, which is 2 by 2. I should point out, notice that in the sort of the compact notation, I never write down the t anywhere. It is there. It is there. Like there's really, this x vector is, x1 of t, x2 of t, x3 of t. Everybody that you're looking at, every one of these vectors is a function of time. I want you to think of t as representing time. Once I have the system in this matrix notation, I'm just going to try to find eigenvalue, eigenvector pairs because that's the game plan here, right? We're going to try to find these eigenpairs to build these solutions with. So let's see if we can do this. To find the eigenvalues, we use so for the eigenvalues, we use our usual chapter 7 materials. This is a good review, something from a few weeks ago. We have to find the eigenvalues by using the characteristic equation. So I'm going to subtract lambda off of the main diagonal of our matrix. That's a little 2 by 2 determinant. So this is the determinant of A minus lambda I, right? And this is a 2 by 2, so I'm just going to go ahead and use my formula for the determinant of a 2 by 2 matrix, which is AD minus BC. So I've kind of written it down right here. See, I guess I don't need the screen anymore. For right now, anyway. Get rid of that. Awesome. So this is not going to scare me too much. It's only a quadratic. I'm going to go ahead and just multiply it out. So when I do that, I'll have a lambda squared that shows up. And then I have a minus lambda and a minus 6 lambda, which makes minus lambda and minus 5 lambda, which makes minus 6 lambda. And then I have 5 minus 12, which is really just negative 7. So we're subtracting 7 there. And as always, we have to set this equal to 0. This is nothing new. We've done a lot of these problems before. This one actually does factor quite nicely as lambda minus 7 times lambda plus 1 equals to 0. And from there, we can easily get our eigenvalues, which are 7 and negative 1. Just to remind you, it's always a good practice to just check those against the fun facts. If you add up these lambdas, it should add up to the trace of the original matrix. So whatever the main diagonal adds up to, your lambdas should add up to that as well. Also, if we take the determinant of this matrix, this is the other fun fact, is that the determinant of this matrix, which is 5 minus 12, negative 7, should equal the product of the eigenvalues, which is also negative 7. So it checks out. It's just always good because, as I've said to you guys before, if these lambdas are not correct, it really makes things frustrating down the road when you start trying to find the eigenvectors and do anything else with it. So you really want to make sure you've got these numbers correct. Do we happen to know yet whether our matrix is defective or non-defective at this stage of the game? It is non-defective. How do we know that? Just by glancing at it. Exactly. There's no lambdas that are repeating here. And that means that every eigenvalue will pull its weight. Remember that every eigenvalue has to give you at least one eigenvector. The issue comes up if you get repeated eigenvalues. Be careful, though. This is just reviewing for our exam next week. Just be careful. If an eigenvalue repeats, it still might be non-defective as well. You have to check it in that case. You have to see, well, does that eigenvalue pull its weight or not? Okay, so we can go back and review that later. That's really from chapter 7. But in this case, we know that these eigenvalues will pull their weight. So let's just take a look at it. Let's start with lambda equals 7. We have to find an eigenvector to go with that. So I'm going to do a little null space for that, if you remember. This means I need to subtract 7 from the main diagonal of my matrix. And if I do that, I'll get negative 6 and 6, and I'll get 2 and negative 2. And it's good to remember that this matrix is always going to fail to be invertible, right? This matrix has to be not invertible. I can actually just glance at it and tell that the 2 rows are multiples of each other. If I took the time to do EROs, one of the rows would get zeroed out. And I don't really care which one. I guess I'll just cross off this one. Doesn't really matter. And then I'm going to be super lazy today, guys, and use my little AB trick. Do you remember that trick? This is the trick where if you're trying to solve a system that just got a single row with 2 unknowns here, that you can just immediately write down the vector as being negative b and a, or if you want to put the minus sign on the other one, that's also fine. So you just don't have to do the whole thing with 3 variables and busting them out and all of that. You can just go straight to this. Yeah. So I'm going to do that here. Now, if I do that with the row that I have left up here, I'll be switching the 6 with the negative 6, and then I'll probably make a sign change. And it would be the vector 6, 6. But you know what? I can always scalar multiply that vector by any scalar. And there's nothing wrong with using 6 and 6. but I just like to make the numbers smaller. So I'm going to use 1 and 1. If all of this is like Greek to you, you don't like it, it's okay. You can still, set up X and Y. Y would be the free variable, and solve for X, blah, blah, blah. We've done this many times. Right. So anyway, but I'm just kind of skipping that and just going straight to my eigenvector. So I have one eigenvalue eigenvector pair already in my hands, and from it, I can build one solution to my system as I've explained over there. Let's write it down. X1 of t would be e to the 7t times the vector 1, 1. That is one of the solutions to my system. Okay. So far, so good? All of this, or almost all of it, is really just the old material from chapter 7. The only thing new is just writing this down. This is the only thing that's new here, guys. Everything else on this board is stuff we did 3 weeks ago, 4 weeks ago, something like that. Let's go to the other eigenvalue, which is -1. And I'm going to do the same thing one more time. I'll do it fairly quickly, guys. We have to calculate a null space here. And for this, I'm going to make a matrix where I add 1 to the main diagonal of the original matrix. So 2 and 6, and then 2 and 6. Again, I'll cross off a row. I know I have to be able to do that. And I'm going to use my AB trick again to go straight to the vector here. I'm going to switch the 6 and the 2, but I'm going to put a minus sign on one of those entries. I think I'll put it on the 2, and I'm also going to cut it in half. So it's going to end up being 3 and -1. Again, I went kind of quickly there, but you can more or less get this eigenvector without too much trouble. And so, Dylan.
You always have to simplify it.
No, you could have left this as 6 and -2. I just try to make the number smaller. Okay, so let's write down our second solution. X2 of t would be e to the -t times 3 and -1. So that's X2 of t. And guys, we only need 2 linearly independent solutions in order to have a basis for the general solution. So I can write down, at this point I'm going to do it here, guys. I'm going to write down the general solution. If you can, if you're taking notes on this, leave a little bit of room on the left here underneath, or to the left of the x of t, because I'm going to come back in a minute and write something in there. But in the meantime, I'm just going to build a general solution of these two. So C1 e to the 7t times 1, 1 plus C2 e to the -t times 3 and -1. And this would be a wonderful final answer for this system. Keep in mind, guys, that this vector x of t is really an entire column of functions. I don't know what they are. So over on the left here, this is optional. You don't have to write this down, but you don't normally, when you're solving it, if you just write x vector of t, that's fine. But just keep in mind, there's really an x of t and a y of t. There's more than one unknown function. You guys remember the example I did before the break? Here's 2 tanks that are connected together with pipes, fluid flowing the 2 ways. You have these unknown functions. Could be the amounts of chemical in the 2 tanks at any time t. Well, that could be what these are, right? This could be, this would be optional, but this could just be A of t and B of t. It could be a physical problem like that. Okay. The other thing is that this is also optional. Okay. The thing in the box is the critical answer, but all these other things are just optional alternatives. If somebody wanted to explicitly, if someone wanted to explicitly know, well, what is A of t? How much chemical is in the first tank? Well, that's coming from the top slot of my vector, right? Because this whole expression here has a top slot and a bottom slot. So another thing you could do, and I'm gonna have to shift down just slightly to write it down. You can write across the top slot of everything and just write it in here. So C1 e to the 7t plus 3c2 e to the negative t. That would be A of t. Right? And then I can also just choose to ride along the bottom slot of everything I see and get the solution for B of t. So C1 e to the 7t minus C2 e to the negative t, that would be the B of t. Right? So if you wanted to kind of draw attention to exactly what the two unknown functions were, this is how you could do it, if that makes sense. Is everybody with me? Now, it can be a little bit hard to get appreciation for these things. I mean, obviously, there's, physical applications I've already kind of talked about, but it would be nice if there was another way to kind of understand what's going on here. And I would like to give that to you. I would like to give you a picture. It's actually something formally known as a phase portrait. And I am going to ask you to be familiar with this for our exams coming up. So let's take a few notes on what's called the phase portrait. When I'm drawing the phase portrait, it is going to be a picture, guys, in the XY plane. Give yourself plenty of room. Don't try to squeeze this into a little tiny space. You're going to want to be able to have a nice visual of this. I'm going to draw a phase portrait. And by the way, this is for 2x2 systems only. So we won't be doing, if the matrix is 3x3 or 4x4, we would have to draw this as a 3x3 problem, a three-dimensional portrait or a four-dimensional portrait. It would be very hard to actually draw that accurately. So I'll restrict my attention here to 2x2 systems only. But the idea is I would like to draw the solutions here. This is the equation for x of t. I would like to draw them. And when I say draw them, let me be clear what I mean. Does everybody understand that what's in this box up here is not one solution to the original problem? It is an infinite family of solutions indexed by C1 and C2, yeah? There's infinitely many solutions there, depending on what C1 and C2 are. We actually have two of the solutions on the board already. This x1 of t, this first solution, well, that would coincide with choosing C1 to be 1 and C2 to be 0. So if C1 is 1 and if C2 is 0, you're going to just get this right here. Let's just come back in the notes and just make a note of that. C1 is 1. And C2 is 0. And I would actually like to draw this solution onto this phase portrait right now. I'm going to draw a picture. So at time 0, which would be, t equals 0 here, you can see that when t is 0, e to the 0 is 1, and I just get the vector 1. I need to draw some tick marks here. Forgot to do that, so we can have a nice way to draw this. So if I plug in 0 for t, I get the vector 1, 1. It's right there. Okay? Now here's the question for you. What happens as t starts to increase? You start your clock. It starts running, right? This vector 1, 1 is being scalar multiplied in front by a scalar that is actually getting larger and larger and larger, right? As t gets bigger, e to the 7t blows up. So actually, after 1 second has gone by, the new value of x1 would be e to the 7th, e to the 7th, which is still along this line y equals x, but it's way out much further than where I'm drawing that dot. The point is, basically what happens, guys, is I'm going to draw arrows on these curves. If you start right here at time 0 and then you let your clock start running, the x1 of t is going to go out this way. And I actually, if I wanted to, I could run time in reverse and imagine t going backwards towards negative infinity. If you think about e to a negative huge number, it's almost like 0. So this vector 1, 1 would be getting crushed backwards in time, I'm kind of running the video in reverse, back to negative infinity, this thing would have started at 0, 0. Can I offer you an analogy for this? Something to think about? I want you to think about this XY plane, guys, as like the surface of the ocean. It's the ocean. And you are dropping a feather onto the top of the ocean at time 0 right here. And what you're watching is, where does that feather go as time goes forward? Well, in this case, if you drop your feather right there, it will go out to infinity along that direction. So the currents in the ocean push the feather along that line, y equals x, out to infinity, right? What I have drawn so far is only one solution among the infinite family that we see here, right? So this is the curve that goes with, C1 equals 1 and C2 equals 0. That's what that curve goes with. Let's look at another one. The x2 of t, this would line up with C1 being 0 and C2 being 1. So now I don't have anything in the first term, but the second term, if C2 is 1, I get e to the negative t times 3 and negative 1, which is exactly this. Now, at time 0, you're going to drop the feather somewhere. Well, if I plug in 0 for t, I get e to the 0 times the vector 3, negative 1. 3, negative 1, guys, that's right there. You drop your feather right there. Okay, and now my question is, as time goes forward, where does the feather go? You dropped it on the surface of the ocean right at this dot. And then as time goes forward, where does the feather float away to? As t gets big, e to a negative big number becomes like 0, which means that this vector 3, negative 1 is getting shrunk down towards 0. This feather, if you dropped it there, would flow inward towards the origin. Guys, you have to draw the arrows on these curves because it shows this picture coming to life as a function of time. And of course, if I went in reverse time, all the way back towards negative infinity, this feather would have been coming from way out at the periphery of the xy plane. So that is a second solution. This is the one that has C1 equal to 0 and C2 equal to 1. Okay? Let's draw a couple more solutions. I'm going to steal some space over here to do a little more scribbling.
Dr. I have a question.
Yeah, go ahead.
Could you explain again the why we set C1 is equal to 0 and C2 is equal to 1?
I'm just choosing those numbers just to show you some examples of the solution curves. It's easy to choose those numbers because when you choose these kind of numbers, you're just picking off the basis solutions that we had originally.
Okay.
But I could do this all day long. I've only drawn 2 solutions here, guys. There's infinitely many. I could also do C1 equal to negative 1 and C2 equal to 0. Well, what would that be? That would be x of t equals, let's see, if I put in negative 1 for C1 and I put in 0 for C2, I just get negative e to the 7t times 1, 1. Now this time when I plug in t equals 0, e to the 0 is 1, and I just have negative of 1, 1, which would be down here. And this time, as time flows forward, what happens is the vector negative 1, negative 1 gets magnified, and this feather is going to float away towards infinity that direction. So this is yet another solution. And if I go in reverse time, it would back up like so. So this would be C1 equals negative 1 and C2 equals 0. That's what curve we have there. Okay. And then I could also do C1 equal to 0 and C2 equal to negative 1. Again, I'm just picking these. These are just a couple of the easy examples, right? If I chose C2 to be negative 1, then my x of t for that set of values would be nothing from the first term because C1 is 0. C2 has a minus on that 3 and negative 1. So it's minus e to the negative t times 3 and negative 1. Right. And when I plug in t equals 0 here, I get the negative of the vector 3, -1, which is actually -3, +1, which is right here. And this guy also flows towards the center and comes from out at infinity, like that. So this would be the case of C1 equals 0, C2 equals -1. And so far, what's on my picture of my phase portrait, which is what this is called, is 4 of the solutions. But you guys are probably wondering, well, what would happen? What happens if I drop the feather like right there? Now, that's not going to be an eigenvector. The eigenvectors are lined up with these 2 eigenspaces. So that point is not going to flow straight to the origin or straight away from the origin. In fact, what happens is, and this would correspond to some other values. This is what Adrian is asking me is, what would be the other, or what Eric is asking. Sorry, I get you guys confused all the time. Eric was asking me, like, why don't I choose C1 and C2 to be this? Well, the point being that that would just correspond to 2 other values of C1 and C2. And it basically is going to be a curve that follows the lines as you've drawn them up until that point. So if I drop the feather there, it's going to float like this. One thing that's very important to notice, guys, as I'm drawing these curves, they never intersect. They never cross each other. If they were to cross each other, then what would happen when the feather gets to the intersection point? It wouldn't know which way to go. These initial value problems always have unique solutions. There should only be one trajectory that a particular feather is going to take. So none of these are going to cross. Let's say I start here. Okay, then this feather is going to kind of trace along the directions of the curves that you see already drawn here. Okay, same thing down here. You're going to get curves that look like this. I always get the question of how many curves do I have to draw? Well, it's kind of just, there is no right answer. This is very subjective as to how many curves to draw. But you want to draw enough curves that you kind of get a feel for the phase portrait. Like, this is the surface of the ocean, and you can see how the currents are. Anywhere you drop the feather, it just follows the path. It traces that curve out. By the way, it's also possible to drop your feather directly at the origin. If you did that, that would be like choosing C1 and C2 both to be 0. And if you did that, the feather would never go anywhere. It would just sit there. And that is a solution to our original system. If x of t and if x1 of t and x2 of t are both 0 forever, it satisfies both of those equations. It's kind of a trivial solution, but it would be a possibility. You could just drop that feather right at the origin and watch it sit there. This is really sensitive, though. If I drop the feather just on this side of this eigen space here, it flows around like that somehow. But if I drop it just a half of a centimeter away on the other side of that line, this feather is going to flow this way. Completely ends up in the opposite direction. So even a small little change in sort of the initial value of where you drop the feather in the first place ends up in the long run in a vastly different behavior of the solution curve, as it turns out. Question, please.
To relate it to the 2 tanks, is that just telling us the initial value of one tank and the possible outcome?
We're actually, so when we drop this feather in, that's like specifying how much chemical is in the both tanks at time 0. And then the extent that it's moving to the right or left is showing me, is affecting how much chemical is in the first tank. And the extent to which it's going up or down is indicative of how much chemical is in the second tank. So there's a right-left motion here and an up-down motion that we're kind of keeping track of. I don't know if this picture looks at all familiar to you, but if you took, well, I think you all did take multivariable calculus. One of the things you would have done in that class is of course, that class is all about looking at surfaces. And there's something called level curves of a surface where you slice through the surface kind of horizontal, flat, and you look at a cross section. And there is a particular type of surface that has this exact type of cross sections, which is something called a hyperbolic paraboloid. I have actually taught this Math 250A quite a number of times myself, and the hardest part is drawing the pictures. And the hardest surface to draw is the hyperbolic paraboloid. It's basically like the shape of a potato chip, or another alternative is a saddle. It kind of looks like a saddle. And in fact, that is the name of this type of phase portrait. So this phase portrait is a saddle. It shows a saddle. During Thanksgiving, I was over in Illinois with my aunts and uncles. My uncle loves horse racing, so we sat there all weekend watching horse racing on TV. I don't know if I've ever done that before, but it got me thinking about this lecture. I'm like, oh, I have to make sure I mention that. Yeah, the shape of the horse's saddle is kind of like this hyperbolic paraboloid, and the cross sections end up looking like this. Yeah. Why is it that it has this kind of saddle shape and not something else? I want to think about what other scenarios could happen. Like, what other kinds of phase portraits could we end up with? And how would that happen? Let me see if I can think about that for a second here. Like, what we notice here, guys, is that depending on where we drop this feather, sometimes it flows towards the origin, and in other initial conditions, it flows out from the origin towards infinity. So sometimes in, sometimes out. It's like it's not clear. It depends on the initial value. Why is that? Why is it that it's sometimes flowing in and sometimes flowing out? We go back into the math that we did. I guess I've erased a little bit of it, but some of it is up there. Do we remember? I mean, I've got the two. I don't even, well, here's x2. x1 was e to the 7t times 1, 1. All right, so for this one, the solutions are flowing out. For this one, the solutions are flowing in. What's really driving that? Like, what's causing the solutions to either flow out or flow in? The eigenvalues, right? This one was corresponding to lambda equals 7. This one was corresponding to lambda equals -1. Do you notice one of them is positive and one of them is negative? That's actually the key. That's actually the key. Guys, so just as a note here, right, that we can make some statements about what these phase portraits are going to look like as a function of the eigenvalues. So my first note is that if lambda1 is greater than 0 and lambda2 is less than 0, which is the scenario we just went over, the phase portrait is a saddle. It will always be a saddle in this scenario. I can change the specific numbers a little bit, of course. It'll tweak the actual phase portrait slightly, but it's going to be a saddle behavior in this case. Somebody in my first class today asked me, well, what if lambda1 was negative and lambda2 was positive? Of course, that's really the same as this. It's just the eigenvalues being listed in the opposite order. That would still be a saddle. This is really just saying, what if one of the lambdas is positive and one of them is negative? So what would be some other possible scenarios? Yeah, they could be both positive, right? Or both negative. Yeah, let's think about that for a second. What if lambda1 is positive and lambda2 is also positive? Now, save a little room to finish the sentence here, but I'm going to draw you kind of over here, maybe sort of a mini phase portrait of that. Guys, if both of the lambdas are positive, then both of the exponentials will be positive. And that coincides with solutions flowing out from the origin, yeah? Your phase portrait you might have one solution going out like that or out like that, but then your second solution would also be going out. They would both be going out. And if you drop your feather anywhere else, it might not be a straight line, but it will wiggle its way out to infinity. This is a perfectly possible phase portrait in the case when both of the eigenvalues are positive. And in this case, the phase portrait will be called a source. We will call it a source. So the phase portrait, I'll just use a Plato symbol here, guys, to save a little bit of writing. This is called a source. When both, like the sun, the rays of the sun is the source at the 0, 0, and everything is going out from that. Yeah, so that's another scenario. That's if both eigenvalues are positive. And then, as he had mentioned, we could have a scenario where they're both negative as well. If lambda 1 is negative and lambda 2 is negative, then let's see, what are we going to get this time? For the third case, where are all of my arrows going to be pointing this time? Towards 0, right? Everything is going to be directed inward instead of outward. In this third scenario, so just make sure you get your pictures lined up here. That's number 2. This is number 3. In this third scenario, you'll have your feather will be coming towards the origin sort of from everywhere, right? It might wiggle its way to the origin if it's not on one of the eigenspaces, but it will definitely come in towards the origin. It doesn't matter where you drop your feather into the ocean right now, it will get sucked in to 0, 0 from anywhere you start. It doesn't matter where you start. And this is called a sink. The phase portrait in this case is a sink. Okay. I get asked a lot of times about how picky I'm going to be about these pictures. Obviously, I want the arrows to be pointing the correct direction. But how many curves to draw and how precise those curves must be drawn, we don't have the time or the really the energy to do a perfect job of this. Of course, you can use a computer these days to draw these phase portraits. So it's not going to be critical to me that you spend hours and hours perfecting your sketches of your phase portraits. But I do want you to know whether you have the behavior of your phase portrait, whether it's a saddle, a source, or a sink. And the important thing here, guys, the important thing is that if I ask you that question on the test, here's a matrix. Now tell me, is its phase portrait a saddle, a source, or a sink? I'm basically handing you almost a freebie. It's almost a freebie because to decide whether you have a saddle or a source or a sink, you don't have to do most of this work. You just have to figure out whether your eigenvalues are both positive, both negative, or one of each. As long as you can do eigenvalues of a 2x2 matrix, remember this is only going to be for 2x2 systems. As long as you can do that, you would be able to answer that question. It's a quick one. It's a quick one. It's a pretty straightforward thing. Okay, I think that's what I wanted to say about that. Are there questions so far?
Is that if it's only non-defective as well?
Right, we're only looking at non-defective systems so far. We are going to get to the defective ones soon, but yeah, that's a good point. Other questions so far? All right, I'd like to do another example. Let's start here fresh. I'm going to do a new example for you, and we're going to see some different things that can happen. But the phase portraits, they sort of bring this whole theory to life. Now we can actually sort of visualize the ocean flowing around with its currents as a function of time. You drop your feather in and it traces out a curve. I think that's pretty nice to be able to have that kind of in mind. Okay, but let's do this example. Let's solve x prime equals a times x, where A is going to be the matrix 9, 29, and then -1 and -1. And let's go into the solution of that right away. We're going to try to start off with our eigenvalues again. So the eigenvalues, I have to take the determinant of the matrix that I get when I subtract lambda from the main diagonal. So I'll subtract lambda off of the main diagonal of my matrix. That's just a 2x2 matrix. Okay, I'm going to go a little quickly through this very first part. The 2x2 determinant formula, as you know, AD minus BC, we've used it a million times by now. 9 minus lambda times -1 minus lambda, and then we have a plus 29 on the end of that. And again, I'm not going to be too afraid of this. I'm just going to go ahead and multiply it out. It's just going to be a quadratic. We'll have lambda squared here. And then I have -9 lambda and plus lambda, which is -8 lambda. And then I have a -9 plus a 29, which is really going to become plus 20, which I now have to set equal to 0. Okay. And this actually does not factor nicely. Of course, it does factor. It just may not factor nicely. To get the roots of this one, guys, I am going to just jump to the quadratic formula because that's the best, easiest way to get the roots, since it doesn't factor nicely. So negative b would be 8, and then plus or minus, and then we have the square root of b squared, that would be 64, minus 4ac, 4 times 20 is 80, and then this is all divided by 2. And when I work this out, well, so I clean this up, 8 divided by 2 is 4. But now some of you are noticing that we have an issue here. 64 minus 80 is actually -16. What is the square root of -16? 4i, which then is being divided by 2. I'll go ahead and cut this in half and write 2i. 4 plus 4 minus 2i. So I have good news for you and I have bad news for you. The good news is it's still non-defective. There is no repeated eigenvalue. These are 2 different lambdas, and you can check them with the fun facts. Doesn't matter that we have imaginary numbers here. You can still confirm that they are correct. So that's the good news. The bad news is that if I go and try and construct my solutions now, how in the world would they, well, I guess we're not ready for that yet. We need to find a corresponding eigenvector, but I'm not feeling too good about what these solutions are going to look like. Let's just check it though. Let's do lambda equals 4 plus 2i, and let's just see what comes out of it. So this is the bad news, is we have imaginary numbers to deal with here. So in my null space work that I'm going to do, I have to subtract 4 plus 2i from the main diagonal of A. So I already have in the upper left corner, I have a 9, and I'm going to subtract 4 plus 2i. That's going to become 5 minus 2i. And then the 29 just stays the same. And then in the lower left corner, the -1 stays the same. And in the lower right corner, let's see, I have -1, but I have to subtract 4 plus 2i from that. So it's -5 minus 2i. Now, I've mentioned this before, that when you have imaginary numbers, it might not look like these 2 rows are scalar multiples of each other, but we know that they must be. They have to be, because this matrix is not invertible. If I did EROs, which I'm not going to do, but if I did EROs, I would get a row of zeros to come out of that. I know that that has to be the case. So I'm going to just sort of sidestep that and just cross off a row. When I draw a line through a row, it just means I'm zeroing it out. And you could actually zero out either of the 2 rows. There's no preference one versus the other. But in this case, I'm just going to get rid of the first row because I don't want to deal with a 29 all the way through the whole thing. Now, this is where the AB trick is especially nice, because you can use it here to write down your eigenvector immediately. And your eigenvector, remember what you have to do. You have to swap these 2 numbers and then do a sign change on one of them. I'm going to take the -5 minus 2i and change the sign of that to 5 plus 2i. And then I'm going to leave the -1 the way it was. when we do this, we will get a solution x of t that is going to look like the following: e to the lambda, which was 4 plus 2it, times the eigenvector 5 plus 2i and -1. Right, this is just the usual, this is what I hope everybody is totally absorbed in now. We're making solutions of this form. And I put in the lambda and I put in the v right here. But there's a problem. There is a problem. If you try something like this and you try to plug a number into your calculator on something that has an imaginary number in the exponent, it will not do it for you. It will give you an error message. You have to go study complex analysis for that. Also, I would have no idea how to graph this. Like, how would I put that on this phase portrait? I mean, it would take 2 variables just to even draw a single complex number. You have to have like a real axis and an imaginary axis, but then you've got 2 slots also. It's actually almost like a 4-dimension requirement here that you would have to have. I would not know how to graph this. I would not know how to plug numbers into this. My boss would not like this. This is not good. We need a real solution. Real solutions meaning without I anywhere in them. So I have to show you how to get that, because this is not going to cut it. If this was a problem on an exam, and this is, I don't know, how many points would it be? This is probably only about 20%, maybe 25% of the work that we have to do here, believe it or not. It's a little bit more than you might think, because we cannot accept imaginary numbers in our answers. So this is why you have to pay attention to me now, because if you stop here, your score is not going to be good enough. You need to make sure you know how to extract real solutions out of this, okay? So the next few steps is just going to be some algebra to show you how to do that, right? So let's just keep going with this. I'm going to break up this exponential as e to the 4t times e to the I times 2t. And then I'll put my vector here again, 5 plus 2i and -1 like that. Okay. Now, we need a little bit of a scratch space here somewhere. Need just a little bit more room, guys. Everybody with me so far? Hanging in there? This is just a little bit technical, but I promise when we get to the end of it, I don't think you're going to think it's that bad. This is just over on the side. This is not the main part of my work that I'm showing you, but I am wondering whether anybody happens to know any kind of a formula for, so here we have e to the I times some value, and I would like to evaluate e to the I theta. Does anybody have any clue what that formula is or know anything about that? The math club in our department, and I've even seen this out on the streets, believe it or not. Yes, I do out on the streets once in a while. And I saw somebody wearing this t-shirt. It had on the front of it, e to the I pi equals -1. It is kind of a cool formula. And it is much celebrated because it involves 3 of math's most important numbers, all in the same equation. E is there, I is there, and pi is there. And somehow this equation is true. And so you'll see this sometimes. I think I saw a bumper sticker once. I hang around with math people, so you can imagine. But there is a nice formula for this. I don't know if you remember in the last chapter when we were getting imaginary roots for our auxiliary equation, like roots that were complex numbers. It ended up giving us solutions involving sines and cosines. And actually, that's what I'm driving at over here. There is a famous result. It's called Euler's formula that that tells us that e to the I theta is actually equal to the cosine of theta plus I times the sine of theta. Now, the way you prove that is a little beyond Math 2. I mean, we could do it, but it's not really what I want to focus on in Math 250B. You use the Maclaurin series. It's basically a power series expansion of the exponential function and of the cosine function and of the sine function. You write them all out using their Maclaurin series. You would have learned about this, by the way, in Calc 2 and when you're studying series and sequences and series. So you can actually write down sorry, not sequences. You can write down series for each of these and just check it out that it works. It's pretty amazing. Obviously, if you plug in pi for theta, you'll get cosine of pi plus I times the sine of pi, which is -1. So it is consistent with that formula. But I would like to use it right here to replace e to the I to t in terms of sines and cosines. So let's come back to the main work here and try to write that down. I'm going to replace this middle part with cosine of 2t plus I times the sine of 2t. But before I get too far along, I want to do one more thing. I would like to also split the vector up into a real piece and an imaginary piece, just like I did in the exponential in front. So I can see that the 5 and the -1 do not have an I on them at all. And then added to that, we can pull the I out from the 2, and there's no I in the bottom slot, so I'll put 0 there. So we can actually write it like that. Okay, what is my goal now? Let's not lose sight of the goal. The goal is that this was unacceptable, and I want to get rid of the I from my answer. So far, I'm not doing too great of a job. The I is still there and there. But let's think about this for a minute. I'm going to erase my scratch now. I've got, something plus something times something plus something. If you guys were back in grade school again and somebody had something plus something times something plus something and you wanted to do something with that, what would you do? FOIL it out, right? I would like to do that here, except I'm not going to FOIL it out. I am going to FLOY it out, as in FLOI. I'm going to FLOY it out, and you'll see why I'm doing this, FLOI, in just a second. I'm going to FLOY this out. It's really FOIL, but in a certain order. So when I do FLOY, I start with the first. So that would be cosine of 2t times the vector 5, -1. And then I'm going to jump to the last. Now, on the last, I'm taking the second part here with the second part here. And does everybody see that I have an I times an I? What is I times I? -1. It's I squared, which is -1. So it's a minus sine of 2t, sine of 2t times 0. So far, I did the first term and the last term. And also, so far, let me just go ahead and I'm going to put some parentheses around that, the first and the last. I'm going to stick a big brace in here. This e to the 4t is out in front of everything. So far, I've only done half of my FLOY, but the good news is that so far, I don't see an I anywhere. Okay? Now, when I keep going and do the outers and inners, the O and the I of the FOIL, the outers and inners, the outside terms and the inside terms, they both do have an I on them. But then the outer is cosine of 2t times 0. And the inner term will have a sine of 2t times 5, -1. 5, -1, like that. And so this is the outer term, and this is the inner term. So this is what I mean when I say I'm going to FLOY it out. FLOYing it out like that. Okay. Guys, I still do not have the I totally gone. But it is now only appearing right here. question is, how do we really get rid of it once and for all? Well, I actually cannot get any further than what I have on the board now. There is no algebra that I'm going to be able to do with this that's going to make the I forever go away. But we do have something else in our back pocket that we have not taken advantage of yet. And that is the fact that there is another eigenvalue that we haven't even looked at yet. Yeah. There is another eigenvalue. And we could take that other eigenvalue and use it to do a similar process. Okay, so let me just do this with you guys. So the other eigenvalue, oh, I should mention before I do this, I'm going to mention that this is going to turn out to be unnecessary and we won't need to know it. But if you really want to master this and feel good about your understanding of it, you might want to write this down or at least make sure you're understanding what's going on here. But what I'm about to do, I can't spell. What I'm about to do is going to turn out to be unnecessary, but I'm going to do it anyway to show it to you. For those of you, especially who like the theory. So the other thing you would do is you would take your other eigenvalue, which is 4 minus 2i. And you might remember from back in chapter 7, this is a good chance to review chapter 7. I said that whenever you have these complex conjugate pairs, once you find an eigenvector for the first eigenvalue, the other complex conjugate eigenvalue will have another eigenvector that is just the conjugate of this one. So the eigenvector for this one, we don't need to do any null space work. We can just write it down, guys, 5 minus 2i and negative 1. Okay. Now, if I then go ahead and write down a solution x of t here, so this would be, e to the 4 minus 2i times t times this vector right here, which is 5 minus 2i and negative 1, right? We would have that essentially. And I can do the same game that I did over here, again over here, right? I'm going to do it much faster this time, but I can do the same algebra. I'm just going to go dot, dot, dot here. We go x of t equals e to the 4t. I'm going to pull that outside of everything. And then what I'm going to do is the same process I was doing over there. I'm going to FLOY out basically the terms that I would get when I expand this apart. There is one little hitch here. Do you notice that you're going to have e to the negative something? We do need to remember, I don't know if you guys, I'm sure you guys know this. If I have the cosine of a negative of an angle, which is what's going to show up in a minute, it's the same as just the cosine of the original angle. This is just from trig. And the sine of a negative pulls out that negative, so it becomes negative of the sine of theta. So, where you see this plus right here, if you were to expand out e to the I times negative 2t, which is what you're going to have over there, negative 2t, then this becomes a minus. It ends up becoming a minus in the middle there. So you end up getting cosine of 2t minus I times the sine of 2t. And then the vector is 5 and negative 1. And then plus I times negative 2 and 0. You end up getting that. Okay. And now you just FLOY it out again. I will just do that really quick here. I'm going to FLOY this thing out, e to the 4t. And then when I do the first, I get cosine of 2t times the vector 5, negative 1. The outers and inners, sorry, the lasts. So this is the first. Next one's going to be the last. The last has a minus I squared. minus I squared. Well, I squared is also -1. So minus of I squared is actually +1. So it becomes plus the sine of 2t times -2, 0, like that. So that's the first and the last. And then, of course, the outers and inners are going to have the I factored out of them. And in this case, it's going to be cosine of 2t times -2, 0, and then minus sine of 2t times 5 and -1. I'm going a little fast through this. I don't want to get dragged down too deep into this. But this would be the solution that we would have if we use the other eigenvalue. So can we come back, guys, to the first one we did? And I'm going to decorate this thing up with a hat on top of it. It's going to be x vector hat of t. That's on the first solution. So go back in your notes just a little bit. I'm going to call that x hat of t. And then over here on the solution I was just working on, I'm going to call this one x twiddle of t. I'm going to put a little twiddle sideways s on it. In some ways, all is right with the world. I had two eigenvalues, and I came up with two solutions. This one and this one. But the problem is that both solutions are bad because they both have I in them. So this is no good, and that is no good. So how am I going to get two real solutions that don't have I in them? Does anybody see a way out of this? If I hand this to my boss, I might get fired. If I hand that to my boss, I might get fired. Both of them have I in them. I don't know how to graph them. I don't know how to plug anything into them, but I need to come up with two solutions that don't have I in them. Can we just kind of look a little more closely at the O and the I part for a minute? The outer inner part here has, well, cosine of 2t and -2, 0. Over there, the cosine of 2t has 2, 0. Here, the I part has a minus sine of 2t times 5, -1. Over there, we have sine of 2t with a plus 5 and -1. Now, guys, can I just remind you that the solutions to these systems forms a vector space, always forms a vector space. That means that it is closed under, what's it closed under? Addition and scalar multiplication. In other words, guys, if I have come up with two solutions, then if I add them together, I get another solution. And if I add these together, the O and I parts are actually going to cancel. You see that? If the O and I parts cancel, they're going to take the I with them. It's going to be gone. It's going to be gone. I'm going to make a real solution by adding together these two bad solutions. Bad plus bad equals good. That's actually what we're going to do. So here we go. All right, we can form. Now I'm finally going to get x1 of t. I am going to take the x hat of t, which was the bad solution over there. I'm going to add it to the x twiddle of t, which is the bad solution over here. And the imaginary parts cancel because they're negatives of each other. So when you add them together, this part will cancel with this part because they just have opposite signs. The 2, 0 here is a -2, 0 over there. The plus right here is a minus over there. Now, there is one little side effect here, which is that when you add the two solutions together, the FL part, the last part, actually gets doubled. because you're counting it twice. I don't really care to double it, so I don't want to have a factor of 2 in this thing, but we have scalar multiplication. We have scalar multiplication. I might as well just divide by 2. And if I do that, my friends, if I do that, what I will get as the answer is simply this part only. The OI part has been canceled completely, and I just get this first part. So this becomes, here's what you really need to know. E to the 4t times cosine of 2t times the vector 5, -1 minus the sine of 2t times the vector 2 and 0. That's it. And so that is x1 of t, and that deserves to be into a box. That's right. You with me? Now, I still need another solution. Remember that we have to have 2 of these. And I've got one solution now that my boss would take. This has no I in it. I could graph this. I could make a phase portrait and draw that curve onto it, right? So this is looking really promising. To get a second solution, and I want to put it over out of the way, so leave a little space because I'm going to put x2 right below x1 in a minute. But the way that you get your second solution, I'll just put this on the side over here, is now you start to get smart about it. You realize, oh, if I added the 2 solutions, I could get the O and the I terms to cancel because they're just literally opposites. It turns out, guys, that if you subtract them instead, which is also legit, if this thing is going to be closed under subtraction just as well as addition, if you subtract them, if you take the x hat of t and you subtract the x twiddle of t, take a look, if you would, with me at the F and the L parts of both terms. Notice the F parts are exactly identical. And notice that the L parts are also identical. I do have the minus factored out here, whereas over there the minus is next to the 2, but you can pull that minus out. And those are identical as well. If I subtract these 2 solutions, the F and the L parts will now cancel. And the only parts that survive are actually the O and the I parts. And you'll get 2 copies of them, just like what happened before. So I'm going to divide by 2. But I actually have to do one more thing in this case, which is I also want to get rid of this I. So I'm going to divide by the I as well. I shouldn't use the word divide. I should say I'm scalar multiplying by 1 over 2i. I'm going to scalar multiply by 1 over 2i. Guys, if I do that, your x2 of t is just going to be e to the 4t times the cosine of 2t times 2, 0 plus the sine of 2t times 5 and -1. This becomes x2 of t. That becomes x2 of t right there. And that is our second solution that we've been looking for, that has no I in it at all. You okay with that? So actually, these 2 boxes here, we could have gotten them just right. The first solution is literally just this part. The F and the L part gives us x1. And the O and the I part, which is this part right here, together with the E, don't forget, e to the 4t is part of everything. E to the 4t times this one, but without the I, gives me x2. What I'm trying to say, maybe I'm not saying it very well, or maybe I'm saying it too long-winded. What I'm trying to say, guys, is that you never need to actually do any of this. My marker is dead. This is completely unnecessary. You don't ever have to do this. You don't ever have to do this. What I'm really trying to say is you can just write down x1 and x2 from here. Just do Floy one time using only lambda equals 4 plus 2i. You never, ever, ever have to even think about this other eigenvalue. It won't be necessary to do it. But essentially, our two eigenvalues for plus 2i and for minus 2i have produced two solutions, which is what we want. Questions here? Of course, the general solution would just be C1 times that plus C2 times that. I suppose I should write that down. General solution. Then we'll take a break. So x of t equals C1 times x1 of t plus C2 times x2 of t, just like that. This is a 1 right here, sorry. I would be okay with you just writing it like that as long as I can see what x1 and x2 are. You can certainly just leave it like so. Not a problem. And we're good to go. Any questions here? There is a question you should probably have. And it's not, will this be on the test? You know that it will. I always like complex numbers. No, the question that you might be asking yourself that I'm going to tickle you with for 10 minutes is, what would be the phase portrait for a system that has complex eigenvalue pairs? What would be the phase portrait? How would you graph these solutions and draw them on a picture? We've already seen the saddle, the source, and the sink. And after the break, I'll tell you that we get something different here. It'll look a little bit different. So let's take 10 minutes though. I'm going to let you guys stew on that for a few minutes and then we'll come back and draw some pictures. We'll take a 10-minute break.
I was important.
I actually brothers.
No, this is minus because I squared. Which gave us a there wasn't in the original vector. I know that it showed up over there. That was, it showed up here only because I was doing all of this unnecessary work. If I ignore this board, you would never have that -2 inside the vector. You can pull it out and that changes this to a minus and then it brings it to the factor. So it is totally.
Oh, I was attacking
I know. That's because of the nature of the eigenvector having been conjugated. But we don't have to worry about it. We can just sit over there and just work with it. Yeah. Oh, yeah. Yeah, I understand. I'll have the video, so you just watch the live. Yeah, take care, feel better.
But one, the $120, $120, but it's always the price. You want the bonus and the price to, I did the math. Okay, I adjusted.
What's it, 2 hours?
I always think it's- But my wife is like, you know, Oh, really? You sorry? Big brains. My brain is like that. It's fine, it's
I took 2 weeks off from the class. I had my senior leader teach the class for a day and then just. Then last year, we didn't have Veterans Day, so we had no holidays, so I just gave those students an extra day for the Thanksgiving. Because I went to Ecuador and climbed these huge volcano mountains in the snow, and I needed 2 weeks to get acclimated and all that, so I was actually on Thanksgiving and the week before Thanksgiving, like half of the month I was out of the country. And somehow we came back in December and everybody was ready to go, so it was fine, but yeah, I know what you mean, 2 weeks would be even better than one.
I feel like I'm still in like a week off.
You know what would happen if you took another week off? Come back even more, like, I've forgotten even more stuff, you'd be completely like a zombie. So I actually think it's good we come back before we get too lazy.
So you went to Illinois?
This time I just went to Illinois, I flew over there and I had some family there. Yeah, we went to St. Louis, so some things to see there, and then I went on, did the turkey trot, and then went to, also drove back through Arkansas. And there's a national park there, and I wanted to go climb something very small mountain there, and visit some sites in Arkansas.
Good snow yet?
No, there was not when we were there, but it was just snowing. Actually, I was worried I was gonna not make it back today because there had been a lot of snow coming through in the Midwest. We drove to the airport kind of an odd time to get me there early. I had to sit at the airport for a long time, but we just beat the snow out. It was good. Yeah. That was a close call. But I have a teaching studio set up also at my parents' house. So I have one in Colorado, I have one there. So in the worst case, I was going to email you guys if I got stranded. It's like, guys, we're just going to have to do Zoom again. But luckily, everything was fine. I got back about midnight last night. It's kind of late, but I made it. I'm kind of tired today, but I can still feed off my energy, and then I just gonna collapse tonight. Sleep in tomorrow, I think. I don't. Wednesday is a pretty easy day. Yeah.
That's
Yeah.
for the week.
Well, that'll be good.
It's basically. I really stayed up late to go in the morning to do something. How do I spell my name again? I don't know. Hey.
What's that? First of all, I want you to clean water. I told you.
No worries. All right, guys, I think I want to get started again. We only have about 20 minutes left, and I want to make sure I kind of finish this whole section. We're basically done with 9.4, but I'm just going to make a couple last comments here, if I could, bring us back together. Just to summarize real quickly, the example I really spent a lot of time on it. You don't really have to spend that much time. Here was the original matrix. We found the eigenvalues. And then this eigenvector was the first one we found that goes with 4 plus 2i. So here's something. I always get the question every semester. The students will ask me, can I just memorize where this stuff gets put into the x1 and the x2? I mean, you can see that. You can see that there's sines and cosines in both. And the vectors are appearing in both. This one's always going to have a minus right here. This one's always going to have a plus right here. And I've seen students try to memorize this and just kind of figure out what goes where and turn off their mind and just kind of plug stuff in. Guys, don't do that. You don't need to do that. All you have to do is ploy it out, right? That's how we came up with basically these two solutions. This was the F and the L, and this one was the O and the I. If you just do the ploy, you don't have to remember anything. You just have to go through the motions of it. So I do not recommend just simply memorizing where to put this number, where to put this number, where to put this vector, where to put this vector in the two solutions. There are people who try to do that, but it's not worth using up your valuable memory slots with that information. Okay, so just ploy it out every time and you should be good. I'd like to talk about the phase portrait for this type of problem. We've got these two solutions here. So let's just continue with this example, and I want to look at the phase portrait because that was something we talked about earlier. Remember that I like to view this as the surface of the ocean. We have our scalar functions x of t and y of t, like so. And let's just take a look at this first solution for a minute, the x1 of t over here. Let's just start with that for a second. I'd like to take a look at this. If we were to graph this, let's think about it for a second. If we ignore the exponential part for just a minute and we look at what's in the parentheses here, what you probably notice is that the only place there's a t is with sines and cosines. And I'm sure you all remember that sine and cosine are periodic functions. They repeat themselves every so often. So if I did not have the e to the 4t here, and I just have this, what would happen is I would drop my feather onto that xy plane, and after 2 pi units of time, actually in this case it would be after pi units of time, the feather would come right back to where it started again. Wherever you dropped the feather in, it would still be back at that spot again. Now that didn't happen with the saddle It didn't happen with the source and it didn't happen with the sink. But with this, there would be some kind of repetition to it. Except that the e to the 4t sort of blows it up. It makes it go out from the origin. So believe it or not, when you drop that feather in over there, at wherever you choose to drop it, what will happen is it will start to trace out a somewhat circular pattern, but it's going to get farther away from the origin because of the e to the 4t. And it forms this kind of a shape, which is better known as a spiral. Exactly. And I'm going to put the arrows on this that are pointed outward, because that is supposed to suggest that the feather would trace out this spiral in an outward sense. This is actually called an unstable spiral. Unstable really meaning that the feather goes out to infinity, right? It goes out towards infinity here. Now, people always ask me, well, should it be clockwise or counterclockwise? And exactly how tight is the spiral? I mean, this is getting way too in-depth for a Math 250B. We could spend a lot of time like getting into the details of what these phase portraits look like. I am going to be perfectly happy if I give you this matrix and I ask you, what is the qualitative nature of the phase portrait, and you say unstable spiral, that's good. Okay. And if you can draw me a picture of a spiral going outward, that's even better. Okay. By the way, if I dropped my feather at a different spot, maybe I drop it here, it will still trace out a spiral, but this spiral will never cross the other spiral. They will be interlaced spirals. And again, that's, as I was mentioning before, the phase portrait curves will never cross each other because the feather has to have a unique path that doesn't get to some intersection point. If I had a different initial condition, the feather would go, again, in a spiral behavior, but not intersecting with any of the other spirals. So that is an unstable spiral, guys. That makes sense? Again, this is really rough. I'm not being, notice I haven't even labeled my axes. I mean, I haven't even drawn the tick marks on my axis. I'm not trying to get a perfect picture here. I just want you to have a rough kind of idea of what the nature of the curve is. That'll be good enough for this class. Okay, we're not going super in depth on this. Okay, there are a couple of other things that can happen. So I'm just going to do what I'll call a phase, maybe a phase portraits summary. Okay, so if lambda 1 is greater than 0 and lambda 2 is less than 0, we already talked about this earlier, that forms a saddle point. The phase portrait has a saddle nature. If they're both positive, then we get what's called a source. This is already in your notes. I'm just kind of summarizing it here. And then if they're both negative, then we talked about that earlier. That's called a sink. So we can have a saddle, we can have a source, we can have a sink. And now we have the case of lambda equaling a plus or minus bi. But what is it, guys? What is it that is making this an unstable spiral over here? Why is the feather going outward from the origin instead of inward or just in a circle or something? Why is it expanding? If I look at these two solutions, what part of these solutions is causing the solutions to kind of go outward towards infinity? Yeah, it's that e to the 4t, right? And the 4, by the way, the 4 is really coming from way back here. It's the a value of my complex number in the eigenvalue. So I want to be clear here, guys. In this case, a greater than 0. In this case, we will get an unstable spiral. Exactly. We'll get an unstable spiral. But you guys could imagine another possibility would have been a plus or minus bi. If a had been less than 0, then how would the picture be different? if instead of e to the 4t, the scalars in front had been e to the negative 4t, if it was a negative number, how would that change what you would draw over here?
Would the arrows be heading towards the center?
Exactly, the feather would be swirling inward towards the center and be getting sucked into the center of that circle, and that is called a stable spiral. So in this case, we have a stable spiral. That is a stable spiral. And the last case, it is actually another scenario, would be if the A is actually equal to 0. So if my lambda values are literally just purely imaginary, if they're purely imaginary, in this case, if there is no A at all, then you don't actually have these exponentials at all. And you literally do get a feather that just keeps tracing its same path again and again. It doesn't go outward, it doesn't go inward, it just goes around in a circle. It is called a circle. That's right. I think there's one of those on the homework actually. So a circle behavior would be if the A value is equal to 0. This is worth memorizing. Again, guys, if I give you a matrix, if I just give you just the matrix and I ask you what is the qualitative nature of the phase portrait, then of course we know what the answer is for this example. The way we got that answer is literally just by coming up with the lambdas. So if I ask you a question about phase portraits on our exam next Tuesday, I am basically throwing you I'm giving you a lob, more or less. I'm basically throwing you a freebie. Not really free, but you know, it's not that hard. You just have to figure out what the lambdas are. You don't have to do any of the rest of this to answer that question. You don't have to do Floyd. You don't have to even find the eigenvectors. You just only need the eigenvalues to tell me what kind of phase portrait you have. Good to go on that? Any questions? Again, this is only for 2x2 systems. Not going to get any more involved than that. Okay, well, I would like to throw one more example up on the board. I really appreciate you guys bearing with me today. I know I've been talking for a long time. My voice, even a week off, I come back, my voice struggles to keep up. But I would like to throw one more example at you before we call it a day. We will not finish this example today, but I at least want to plant the seeds. You know, my soap opera style of lectures. I have to give you a reason to come back on Thursday to see maybe something that's a little different than what we've talked about already. So let's say I ask you to solve x prime equals a times x, where the matrix A is going to be a 2x2 matrix again, 0, -2, and then 2 and 4. Let's take this one. And at first, it may not look terribly interesting. It just looks like more of the same thing again, but wait till we start solving it, and you'll see a difference pretty quickly here. So let's start trying to solve it. We would start the same way as we always do. We're going to find the eigenvalues of the matrix. That means I have to subtract lambda from the main diagonal of this matrix. I'm going to subtract the lambda off of the main diagonal, and this is what we would have. And again, it's just a 2x2, so I don't mind using the 2x2 determinant formula. Negative lambda times 4 minus lambda, and then we have to add 4. And if we multiply that out, it should give us lambda squared minus 4 lambda plus 4. And this actually is a perfect square. It is actually lambda minus 2 quantity squared. And if I set that now equal to 0, I'm about to get my lambdas. Let me give myself a little more room here. I'm going to get my lambdas, and my lambdas are going to be 2 and 2. And we can, of course, check them against the fun facts, always a good idea, right? They add up to the trace of the matrix. The determinant is 4, okay, that's the product of the lambdas, okay, so it seems reasonable. So those are the correct lambdas. Now, based on this, do we know whether the matrix is defective or non-defective? We actually don't know yet. When there's a repeated lambda, again, please don't get mixed up about this. When there's a repeated lambda, it still might be non-defective. That is still a possibility, but we would need to check whether this eigenvalue pulls its weight. And for that, we do have to do this null space. So I'm going to subtract 2 from the main diagonal of the matrix, and I'll get -2, -2, and then I'll get on the second row 2 and 2. Okay, it's going to be something like that. And of course, I'll cross off a row. I know that these 2 rows are multiples of each other. I'll cross one off, and I'm going to go straight to my eigenvector. I'll use my little AB trick, and I'm going to also cut the vector in half with a 1/2, and I should get a vector of -1, 1. And now we actually know that we are in trouble. We are in trouble here because this eigenvalue had a weight of 2. We wrote it down twice, and yet it only produced 1 eigenvector, which means I can only make 1 solution. I'm going to go ahead and write it down. There is 1 solution that we can write down here, which is x1 of t. It's e to the 2t times the vector -1 and 1. So we can write that down. But here's the problem, guys. The problem is we have to have 2 solutions. And we only get 1. We don't have another eigenvector to work with here, right? So that becomes a big issue. How can we get a second solution to this? The real problem, let's go back kind of to the top of our notes here. The real problem with this example, guys, is that this matrix was defective. And the topic of this section is, I'll go ahead and go back to the top here for just a moment, the case where A is defective. That is what we're starting to talk about. It's defective, so we don't get enough solutions. We need a second solution, we only had 1. Now, you might remember something like this happened before. Back in chapter 8, if we had an auxiliary equation and we had some root that got repeated, I basically gave you a quick answer for how to deal with that. In chapter 8, we would write down, in that case, everything looked a little different. You'd write down e to the -5x. Does any of you remember what I did for repeated roots in the last chapter? Stack those x's, exactly. So I just stack an x, and then for the next one, I just stack another x, so it becomes x squared. And that was easy enough, right? So what people often try to do here, which turns out not to work, is to just stack a t into another solution of this. You can't actually do that. It turns out that we need a better guess than that as to how to create this second solution. Somebody way before I was here, way smarter and more creative than me, figured out how to make a second solution that would work, and it has the following form. Let me write it down over here. It turns out the answer is that we guess a solution of the form. So this is the form that the x2 of t is going to have. And by the way, guys, be sure that you're here on Thursday, because the notation I'm going to use is not quite the same as what's in the book. The book tries to be really general with it, but I'm going to just do some fairly easy cases here. What we do is we take our e to the lambda t, and instead of putting an eigenvector at the end of this, which is what we were doing up until now, what we have to do here is put in this thing that is going to be w1 plus t times w2. where, so that's the quantity of W one plus C times W two. Where W one and W two are to be determined. They are to be determined. So I'm gonna have to explain how you figure them out. So this is something you're gonna wanna make sure you memorize. The idea is going to be to plug this thing into both sides of our big linear system, which is our $1 million problem of this chapter. I'm going to take the derivative of that x2. I'm going to set it equal to a times x2. I'm going to look at the left side. I'm going to look at the right side. I'm going to match them up. And by doing that, I'll be able to say something about W1 and W2. So that's for another day. We need a little more time on that. Also, I'll do some 3x3 examples on Thursday for this defective section. There's quite a bit to it. Make sure you're here. You'll want to see it. Any questions before we go? I think we're out of time for today. Guys, have a great rest of your Tuesday. And I will see you all again either in my office hours later on or else Thursday. Bye for now.
Yeah,